All of you can you see the screen?
Yes, sir.
Right, so we'll continue with the damped vibrations. And we have discussed the theory behind various types of vibrations. And we are started with the discussion on viscous damping. And as you are aware, viscous damping is done by due to some viscous fluid. Okay, so we have started the discussion. We derived the equation for the damping coefficient, and then we are working on some examples. I already sent the notes to you. This is the first example, a railroad bumper. Everybody has the notes.
Yes, sir. We have the notes.
Alright. So a railroad bumper is designed with a spring and viscous damper in parallel. What is the damping coefficient of the bumper such that the damping ratio is 1.25? Okay, so it is an overdamped system. It is already given. The railroad car which engages with the bumper has a mass of 20 tons and stiffness of the bumper is 2 into 10 raised to 5 Newton per meter. If the railroad car is traveling with a velocity of 72 kilometers per hour when it engages with the bumper, what is the maximum deflection? Right. So let's start. Let's draw it as some kind of a reference diagram. This is a railroad bumper of sorts. And it is traveling with 22 kmph, and it is hitting a damper system. Stiffness is K, damping is C. So zeta is 1.25. It is overdamped. K is 2 into 10 raised to 6 Newton per meter. C is what you will find out. Mass is in 20 tons. So that is 20,000 kgs. Omega n is equal to square root of K by M. That is equal to 3.16 radians per second. Correct? So substitute K and M, and then you get this omega n is equal to. Then let's calculate. What do you say? Calculate damping coefficient. So that is C. Zeta is equal to 3 divided by Cc, or C is equal to zeta into Cc, that is equal to zeta into 2m omega n. So substitute the values. So this comes out to be 150 into 10 raised to 3 Newton second per meter. Second, you have to calculate the maximum max deflection in bumper. Right? When it strikes at 72 kmph. So initial velocity x0 dot is 72 kilometers per hour. That is equal to 20 meters per second. Initial displacement x0 is 0. System is over. So the approach that I am taking is I am deriving the whole thing. I am not going to do formula substitution because it will be difficult. If it was a real exam, it would have been difficult for you to remember this equation. So these are the roots of the, since this is a overdam system, these are the roots of the governing differential equation that we have already given. So S1, so it comes out to be minus 1.58 and S2 is equal to minus 6.8. Questions till now? Alright, so we have done the derivation of underdamped and critically damped system. We have not done the derivation of overdamped system. I have directly given you the results. You are free to solve and check it. So here we are doing an example of for a overdamped system. Alright, so even though the derivation is not given, derivation is not likely to be asked, but definitely numericals will be asked. Okay, so the solution of this now equation becomes C1 e raised to S1t plus C2 e raised to S2t. And use C1, C2 or A or B. Doesn't make any difference. Then you go to C1 e raised to minus 1.58 into T plus C2 into e raised to minus 6.32 into T. Okay. Now substitute both the boundary conditions. So x at t is equal to 0 is equal to 0. So that becomes C1 plus C2 is equal to 0. X dot at t is equal to 0 is 20 meters per second. So that becomes 1.58 minus into C1 into e raised to minus 1.58 into t plus, sorry, minus 6.32 into e raised to minus 6.32 6.32 t into c2. Alright, so substitute t is equal to 0 in this equation. So now we get another equation 20 is equal to minus c1 minus c2 minus 1.58 c1 minus 6.32 c2 or 1.58 c1 plus 6.32 c2 is equal to minus 20 and c1 plus c2 is equal to 0. Alright. So substitute the values and find the values of c1 and c2. When you solve this, this comes out to be 4.22 and this comes out to be minus 4. So these are neat values. Alright, so substitute that in the equation of the time and we get the equation for the displacement xt is equal to this. This is the equation. Now we have to find out x max. So how will you find out? Anybody? Hello?
Displacement is maximum when velocity equal to 0. So we can solve for h dot equal to 0.
Right? So correct. As somebody has said, Abhishek Mishra, I think. Correct?
Yes, sir, Abhishek.
Okay. So displacement is when x is equal to x max, x dot, the derivative of this equation should be equal to 0. Alright. So let's take that derivative. So x dot is equal to 0 and equal to 0 and find the corresponding time and that T max comes out to be 0.292 seconds. Okay. So that is the so then substitute this T max in the equation of displacement. So substitute T here as T max that is equal to 0.292 seconds and that will give you x max and that value comes out to be 2.0. So such sums can be asked where the where the damping is overdamped. Okay. Any questions? All right. So have you also received the two quiz links? Hello.
Yes, sir. We have received the links.
Oh, so those are the at the end of the lectures. You have to solve those two quiz, and this quiz will be based on the numericals which I am solving currently in the lecture. And I think the first question is based on this one, this question. Okay, so starting from here, we are going to search. Okay. Okay, so derive the equation of motion and find the natural frequency of the vibrating system. So that is the question. So let's construct the free body diagram. We have a sphere is rolling on a surface, and let's assume that it is rolling to the right. Okay, this is the point of contact. Okay, that is the instantaneous center. So angular displacement is theta. Theta dot is the angular velocity, and theta double dot is the angular acceleration. Okay, so let's construct the free body for this. So mark the forces. The forces will be the damping force, Cx dot, and the spring force, that is Kx. So since I have marked only forces, I'm going to solve it using the D'Alembert principle. So summation MO is equal to I0 theta dot theta double dot, and that is clockwise positive. Clockwise moment is positive. So both the moments are negative. So minus Kx, radius of this disc is minus Kx into R minus Cx dot into R is equal to Mi about O is Mr square by 2 plus Mr square, parallel axis theorem, into theta double dot. Alright, or I can write 3 by 2 Mr square theta double dot plus Cx dot into R plus Kx into R is equal to 0. Now x is R theta and x dot is R theta dot. So our equation becomes, so let's convert all this equation into terms of theta. So this becomes 3 by 2 Mr square theta double dot plus Cr square theta dot plus theta is equal to right. So our standard equation, if you see, it is I equivalent into theta double dot plus C torsional equivalent into theta dot plus K torsional equivalent into theta. Okay. And this is equal to 0. So if I want to find natural frequency, what is the natural frequency? Yes, anybody? What will be the natural frequency?
Sir,
K
K by M
torsional equivalent upon I equivalent. K torsional equivalent upon I equivalent.
Who is that?
Deepak.
Deepak. SAP ID?
27.
27. Alright, so that is, so substitute, so K torsional equivalent is the term which is the coefficient of theta, and I torsional equivalent is the coefficient of theta double dot. So substitute that and you get omega n is equal to 2K by 3m. Alright, so that is the natural frequency. So let's do some more examples on similar topics or similar systems, not topics, similar systems. So derive the equation of motion and find the natural frequency of the vibration for each of the system, not system, each of the system for the system shown. All right. So first step is to draw the free body diagram. So let's draw the free body diagram. All right. So let's assume that this is moved with angular velocity theta dot and theta double dot acceleration. Okay. And the point of contact is O, and that is the instantaneous center. That is this point. All right. So forces.
Sir.
Hello.
Sir.
Yes.
Sir, will there be always given the direction of x, like in this problem and previous one we are given the direction of x? So is the case with every problem?
This is also. It need not be always downwards. See, this system is oscillating. It is going back and forth like this, up and down. All right. So if you take down, then we have to mark theta, theta dot, theta double dot in clockwise direction. Then the forces will be in opposite direction. So for example, now I am marking the forces. Now the forces will be parallel to the ground. So this will be kx and another spring over here. So another kx and plus there will be the damping force Cx dot. Okay, so that is the free body diagram. The Kx, so plus Cx dot, that is due to the second spring. Second spring mass damper system, like this system. Correct. So now write the D'Alembert equation summation n is equal to I0, summation Fo is equal to I0, theta double dot, clockwise positive. So what does that give me the so again I have to write the equations. So substitute the forces, take moment with purpose. So kx into r minus kx into another r minus cx dot into r is equal to I0, that is at whatever is 3 by 2 mr square theta double dot. So again I am going to substitute x as r theta and x dot is equal to r theta dot, and I will get the equation that is 3 by 2 mr square by theta double dot plus c r square theta dot plus 2k r square theta is equal to 0, which is again of the form I equivalent into theta double dot plus c torsional equivalent into theta dot plus k torsional equivalent into theta is equal to 0. And again our natural frequency will be k torsional equivalent divided by I equivalent. So once you figure out the free body diagram, rest of the steps are trivial. Important thing is to figure out the how to construct the correct free body diagram with taking into account all the possible forces. Okay. Any questions?
No, sir.
Oh, so let's go. If you have any questions, please ask me immediately. Yeah? So there will be quiz based on each of these questions. Huh? So derive the equation of motion and find the natural frequency again. So this is a different kind of system. This is like a rod. All right. So let's construct a free body diagram for this. So actually this will not be given. Huh? The direction of motion it should not be given. You have to assume that. So this is in clockwise direction. We'll use a different color because a lot of stuff is going to come. So I'm going to use a slightly different color so that it's distinguishable. But this is theta, theta dot, theta double. Back to the original color. All right. So now let's mark the forces. So forces will be, so let's construct the free body diagram. very important to understand the concept of free body diagram here. So this will be 3k into x. All right. And see here it is given this is L by 4 and this is also L by 4. So displacement at, let's call this as A, B and C. Displacement at A and B will be same, right? So if I just project this down, then there will be a force in the opposite direction, that is Cx dot. Okay, but at point C, the force will be again opposing the motion, but the displacement now it is x. It is not x. So this is, if this is x, if this is x, then this is also x. But this will be not x. It will be something different. So x1. So this force will be k into x1. So what is x1? What is x2? What is x? That we interpret in terms of theta. All right. So now I have the free body diagram. Now let me construct the what do you say, the D'Alembert's equation. So summation m is equal to I0 theta double dot. Let me draw the free body diagram real quick. Yeah, this is the pivot. Here one. Change color. Forces are, this is Cpx, this is Cx dot, and this is Kx1. This is L by 4. This is also, and this is L by 2. And this is theta dot. So now right side the equation. So that is minus 3kx into L by 4 minus Cx dot into L by 4 minus Kx1 into 3 L by 4 is equal to I0 theta double dot. Now x is equal to L by 4 into theta. X dot will be L by 4 theta dot. So will be 3 L by 4 theta. So let's substitute all these values in the equation and convert this entire equation in terms of theta. Okay. Now I have written this entire equation in terms of theta, which is of the similar format. So it is in terms of theta, theta dot and theta double dot and its coefficients. Okay. So now if I arrange this equation in our familiar format, so this becomes I0 theta double dot plus CL square by 16 into theta dot plus 3 by 4 KL square theta is equal to 0. So again it is of the form I equivalent theta double dot plus C torsional equivalent theta dot plus K torsional equivalent is equal to 0. Alright, so n is square root of K torsional equivalent by I equivalent. Now K torsional equivalent is equal to 3 by 4 KL square. I equivalent will be I0, I self, that is ML square by 12 plus the parallel axis, that is m into L by 4 whole square, that is ml square by 16. So that comes out to be, I equivalent comes out to be 7 by 48 ml square. Alright, so that is the, so substitute all this I equivalent and P equivalent in this omega n equation, and you get omega n is equal to 36 k by 7. Any questions? Fairly simple. Once you know how the technique of drawing the free body diagram, then everything becomes very simple. Okay, can I continue with the next question? Can I continue to the next question? Hello.
Yes, sir.
All right, let's continue on. Let's go to the next question. So here, again, you have a spring mass damper system, and you have to construct a free body diagram. So let's construct this. So you have to find C if damping ratio is 0.2. And in the quiz, some other questions are also asked based on this question. So let's first draw the free body diagram. This is 0.0. All right. Now I am going to, let's take it this way. Theta, theta dot. Use a different color. I'm sorry, it is not this way. It is this way. No, it is this way. Yeah. So this is theta, theta dot. So now all the forces will be in opposite direction. So force. So this will be so if this is theta, so this will be this. So here the displacement is x1. Spring force is kx1. So here also the spring force will be how much? Kx1. Here where x1 is equal to, this is radius is r, so x1 is 2r theta plus r, that is 3r theta. Any questions?
So,
Yes.
so the kx at the center will be due to the string tension.
Yes.
Okay.
The kx1, no?
Yes, sir.
Everybody agrees with me on this equation for x1? Can anybody elaborate how I got these two terms?
The above one will be
Okay,
2R
okay. What is X?
deflection.
What is X1? Can somebody tell me?
The total deflection of the springs.
Okay, who is that? Deepak.
Yes, sir.
Oh, total deflection of the spring. Total deflection. All right. Okay. So how do I get this as why this two R theta and R theta?
So deflection at top and the
At
deflection at the
center
center.
it is R theta and above at top it is 2R theta.
Okay. So this is two R theta. And is anybody else who would like to answer? Somebody else was asking.
The deflection at the center will be r theta and the top will be 2r theta.
Name? Name SAP ID?
Manan.
Manan.
Manan 59.
59. All right. So this is 2R theta and this is R theta. So the spring is getting pulled from both the sides. And so total deflection in this spring is at the one at the top plus one at the bottom. So X1 becomes 2R theta plus R theta. So that is equal to 3 theta. Okay. Then deflection of the damper or the displacement of the damper is x2 and velocity is given as cx2 dot. Okay. So what will be x2?
R theta dot.
X2 will be r theta, x2 dot will be r theta dot. Okay, so x2 is r theta and x2 dot is r theta dot. All right. So these are all the forces. Just okay. So this is the complete free body diagram. All right. Now once the free body diagram is done, then the next steps are really trivial. So let's do that. So next is to write the DLMRs. That is summation m 0 I 0 theta double dot and this is clockwise positive. So that is equal to minus k into x1 into
2R.
correct 2r minus k into x1 into r minus px2 dot into r is I 0 theta double dot. So again my equation becomes I 0 theta double dot plus so x1 is 3r theta. So substitute that 3r theta and x2 dot is r theta. So I0 into c r square theta dot plus total is how much?
Sir, 9k theta square.
9k.
Theta
So always place the coefficient on the left hand side of the variable. Okay, so theta is the variable. So should be the rest of the stuff should be on the left hand side of it. So 9k r square theta. All right. So again, this is our familiar format which we want I equivalent theta double dot plus c torsional equivalent theta dot plus k torsional equivalent theta is equal to 0. All right. So I equivalent is mr square by 2, sorry, small r, mr square by 2 plus mr square. So that is equal to 3 by 2 mr square.
So,
Yes?
so in the free body diagram,
Huh?
so we took the deflection and we added the both deflection of the top spring and the bottom spring.
Huh.
Can we take it different x1 and x2 and then we can solve this?
But one thing, no?
So because I'm not understanding why we took the deflection in the same x1 and added.
System moves to the left. Okay, that I will explain.
Yes, sir.
System moves to the left.
Yes, sir.
Alright. So the deflection of the top point is what? 2r
2r
theta.
theta.
Deflection of the center is what?
R theta.
R theta. So now what is happening? Spring is between in here, and both the points are moving on to the left hand side. So the spring is getting stretched from both ends. Alright. So if I just construct the free body diagram of this spring, free body diagram is a very powerful tool. Alright. So this is R theta, and this is 2r theta. Okay, so the spring is getting pulled on both sides by this deflection. So total deflection in spring is what?
Okay, so because it is of the same spring, we are adding it.
Yes.
Okay, okay.
Alright, and so here now about the forces. See, this spring is passing. It is attached to string on both sides and is passing over spool speed. So the force in the spring is what? Internal force will be stiffness into deflections. And deflection is 2r theta plus r theta, that is 3r theta. Alright, so here this forces, which is these are the internal forces. So these are the internal forces. So internal forces is what? K into x1. Here also K into x1.
Yes, I understood.
Okay. Because it converges. Alright. So what is asked is the C torsional critical. So C torsional critical, if you remember the equation, it is 2 square root of 2 into m into omega m into k. Alright. So for torsional equivalent, it will be 2. This is the equivalent of m. This is the equivalent of k. Square root of 2 km. Alright. So CC is what? 2m omega n. Okay, omega n is k by m. So this is m into square root of k by m. So this becomes 2 into square root of k m. So so this is 2 into square root of k m. So equivalent of k is k torsional. Equivalent of m is inertial. All right. So everybody understood how I got it? Hello. So substitute the values of I equivalent and K torsional equivalent and tell me the answer. You can post the answer on the recent chat box. Everybody's calculating? Are you guys calculating?
Yes, sir.
Alright. So C torsional critical will be
6r square under root 3 by 2 mk.
yeah. So just simplify this and tell me this number into bracket r square into square root of km. So tell me this number.
6 under root 3 by 2.
Yeah. But that everything I have taken out. The numerical part I have taken out, and just tell me what will be the coefficient.
7.35.
7.35. That's the correct answer. Okay. And what is the damping ratio given?
Sir, 0.2.
0.2. So torsional equivalent divided by C torsional critical is 0.2. So So C torsion equivalent is how much? Can you
Sir, CR square, sir, na?
CR square, correct? And C torsional is this value. So substitute that this value C torsion critical into 0.2 and tell me the value of C in terms of root of K.
So 1.5 I'm getting.
1.5, correct? 1.5. Now let's try energy method to solve this equation, and let's see if our whether the solution becomes more complicated or is it becoming simple. Energy method. All right. So energy method will be kinetic energy plus potential energy is equal to constant. All right. So kinetic energy will be half I0. So I'm completely converting this into about O. So half I theta dots I0 theta dot square plus potential energy of the spring half K square plus the potential energy stored in the damper. So that is equal to integral of FD dot dx. All right. And here x will be x2. So dx will be dx2. Okay. And damping force will be C into x2 dot.
H2. So minus na?
Pardon?
Will we take the value as minus CH2?
No, why minus CH2? Why minus?
Because sir, in the diagram we took in opposite direction.
See, now we are doing with energy. That was for
Yeah,
real numbers. Okay, so here we just write the energies. Okay, what is the potential energy which is stored in the system and what is the kinetic energy? Alright. So
Yes,
now
sir.
our equation again substitute the values of x1 and x2 in this equation. So this becomes half I0 theta dot square plus half K into 3r theta square plus integral of cx2 dot into dx2 is equal to constant. So x2 is nothing but r theta. So x2 is nothing but r theta. So dx2 will be r d theta. Okay. So I will write half I theta dot square plus half K into 9 r square theta square plus integral. So I'm going to take some of the terms outside. So x2 is equal to x2 dot is equal to r theta dot. So this becomes c r square theta dot d theta is equal to constant. Right? So this now I want this in terms of integral of time. Okay. So what I'm going to do instead of writing it as d theta, I'm going to just write it d theta by dt into dt like this. So basically it remains same. This I'm just going to manipulate so that it becomes a differential time into constant. All right. So this term again becomes dot. So my term becomes half I theta dot square plus half 9k r square theta square plus c r square into theta dot square dt is equal to constant. Okay. So what will be the next step? Differentiate this equation. Okay. So when I differentiate this equation, this becomes I theta double dot plus 9k r square theta dot plus derivative of this will be simply c r square theta dot square. Okay, derivative of this integral will be theta dot square is equal to 0. Alright. So now eliminate theta dot from everywhere. This theta, this one goes, and this one goes. So when I simplify this equation, this becomes the differential equation becomes I0 theta double dot C r square theta dot plus 9 r square theta is equal to 0, which is the same differential equation which we had got earlier. Okay, so you can do this by energy method also, but you just need to apply the equation correctly. All right. Any questions?
No, sir.
All right, so I will just take just a minute and just come back in a minute. All right, let's continue. Let's continue with the next example. A heavy door along with a closing system is shown in the figure. The moment of inertia of the door panel about the hinge axis is 20 kg meters square. Stiffness of the torsional spring is 25 Newton meter radian. Find out the suitable value of the damping coefficient C. Neglect the effect of inclination. Okay. So here this distance A is given, and that A is 10 centimeters. So we have to find out the find out the most suitable value of damping coefficient C. That is what they have asked. Okay. Neglect the effect of inclination. So first thing, let's construct a free body diagram. So let's do that. There's a hinge at the end. This rod. And there is this Cx dot. This distance is A. Okay. And this is in counterclockwise. Theta, theta dot, theta, double. Okay. So write the D'Alembert's equation. Summation M is equal to I theta double dot. So here you have a torsional spring. Okay, let me just correct this. This is the displacement, and then you have here, if you see the diagram, you have a torsional spring over here. Okay, so this is a torsional spring, like the one which you have in the toys, something like that. Okay. So the torsional spring, so this is in clockwise, it will exert a moment in opposite direction. Okay. So there will be a torsional force in opposite direction to that of the motion. So that will be equal to K torsional into theta. Okay. So this torque is acting in opposite direction. So that has to be taken into account. So it is KT into theta minus Cx dot into A is equal to I theta double dot, where I is equal to I hinge. Right? Where is that is where the rotation is taken. So I can write this as I theta double dot plus C. And now X is equal to A into theta. All right. So X dot is equal to A theta dot. So I can write I theta double dot plus K torsional. Sorry, let me write the damping equation first. So that is X dot is A. So C A square theta theta dot plus K torsional into theta. Okay. So C torsional equivalent is equal to A square C. Right. And for a critically damped system, this will be equal to C torsional critical. All right. And what is C torsional critical? 2 into I equivalent into K torsional equivalent. All right. So substitute the values and find out the value of C. All the values are given in the equation. Substitute all the values and tell me the value of C and post it on the chat box. Is anybody calculating?
Yes, sir.
All right, so many of you have got it correctly. So C torsional, so C value of C is 4472 Newton second per meter. All right. So now let's see if we can solve it by energy method. So energy method, we write the kinetic energy, that is half I theta dot square plus the energy stored due to damping, that is damping force Fd into dx plus the potential energy stored in the torsional string, that is half k theta square. Half kx square for torsional becomes half k theta square. Right? And this thing is equal to constant. And so this again becomes half I theta dot square. Fd is Cx dot damping force, and this is dx plus half k torsional into theta square. Now x is equal to a theta, so x dot is equal to a theta dot, and dx is equal to a d theta. All right, so here again I am going to write it in the form of that in terms of theta. So my equation becomes half I theta dot square integral C A theta dot into A d theta plus half K T theta square is equal to constant. All right, so this becomes, now again I am going to write this d theta as d theta by dt into dt plus the rest of the stuff. So this becomes half I theta dot square plus C A square theta dot square dt plus half K torsional into theta square is equal to constant. Now differentiate this equation. So this becomes I theta double dot plus C A square theta dot square square theta dot square plus dot plus into theta double dot plus C A square theta square plus K torsional into theta dot is equal to 0. So cancel out theta dot. So this becomes I theta dot double dot plus C A square theta dot plus K torsional theta is equal to 0. Alright, so which is the same equation which we have got earlier. So that's how we can solve it using the energy equation. Okay, just simplify this. This is I theta double dot into theta double dot C torsional equivalent into theta dot plus K torsional equivalent into theta is equal to 0. This is the Raoult equation, which is same as we got by using the DLM function. All right. Okay. Any questions?
No, sir.
All right. So let's continue. Next question. The successive amplitude of a vibratory system as obtained under free vibrations are 9 degrees, 6 degrees, 4 degrees, respectively. The MI of the torsional pendulum is 600 kg meter square, immersed in a viscous fluid. The shaft diameter is 10 centimeter, length is 40 centimeter. A reference small diagram is drawn over here. G is modulus of rigidity for the supporting staff, that is 4.4 into 10 raised to 10 Newton per meter. Find the logarithmic decrement, the damping torque per unit velocity and time period of oscillation. All right. What do you mean by damping torque per unit velocity? Can somebody tell me?
Shear force.
Torque upon the velocity that is moving about.
Pardon?
The damping coefficient for the torsional movement upon the velocity. Upon the
It is
velocity.
torque per velocity. So in this case, it will be angular velocity. This is nothing but the damping coefficient. Okay, just a different way to state it, but it is the damping coefficient in torque shaft. All right, so let's go to the next step. So let's summarize the data. So diameter of the constraint is 0.1 meter, length is 0.4 meters. Modulus of rigidity is 4.4 into 10 raised to 10 Newton per meter square. Polar MI is pi by 32 into d raised to 4. That is equal to 9. So substituting d over here, this comes out to be 9.82 into 10 raised to minus 6 meter raised to 4. K torsional is G into J divided by L. Omega n is K torsional divided by I. Okay, and that is given as, so this MI and this MI are different. Okay, this is area MI, J is area MI, I is the mass MI. Okay, and this is given as 600 kg meter square. So find out KT, substitute in the equation and tell me the value of natural frequency.
So 42.4 amplitude.
Correct. So natural frequency is 42.43, not mm, radians per second. All right. Okay. Now let's go to the next part. So this is the type of oscillation. So what if you see the ratio of successive amplitude, that will be 9/6, and then it will be 6/4, and this is constant. Okay. So what kind of system is this? Can anybody tell me? Under. It is a underdamped system. Who answered that question? Same. Okay. So what will be logarithmic increment? Natural log of.
X1 upon X2.
So these are all thetas.
Okay, X1
Theta one by theta. Alright, so any adjacent ratio, adjacent amplitude, and you have to take a ratio, and that comes out to be 0.05. Okay, and that is equal to twice pi zeta upon square root of 1 minus zeta square. See, it is a torsional system, but the equations will remain the same. Or I will get zeta is equal to, if I rearrange the terms, I will get it as zeta is equal to del divided by square root of 4 pi square plus del square, and that comes out to be. So find out. Okay, so this is your logarithmic decrement. That is one question which is asked. Then they are asked you to find out a damping coefficient. So damping coefficient Ct is equal to C torsional critical into zeta. So C torsional critical will be 2 into I into omega n, and this multiplied by zeta.
So zeta is 6.5 into 10 raised to minus 2.
Yes. So it comes out to 0.0645. And tell me the value of damping coefficient, that is torsional damping coefficient.
So 3055.
3055. What are the units?
Units Newton meter second per radian.
Newton meter second per radian. Okay. That's it. Somebody is reading at least the notes. Okay. So this is your what do you say? Damping. What else is asked? Time period.
Damping ka time period.
Time period of damped oscillation. So how to find out?
So 2 pi by omega.
2 pi by omega d. Omega d is not given, but you know omega n, you know zeta. So omega n into square root of 1 minus zeta. So that comes out to be 0.148 second. All right. So we will last numerical of the day. After that, you have to solve the quiz, and you can submit it, and then you can leave the lecture. Okay. So let's read the question. So this is a question on a here used to have that ammeter, voltmeter. Okay, so earlier it used to be analog instruments. So it is an instrument based. This is a question based on that. Okay, so there is a rotor. Okay, so this is like a dial indicator. Like you have some kind of gauge. If you have seen any dial indicator, like the one which you used to check the pressure in tire pressure. If you have seen it in the mechanic shop, there is a dial indicator. So it is something like that. Okay, so it is a dial indicator connected to a torsion spring. So below this this arm, somewhere here below this arm, there is a torsional spring attached like this. Okay, and a torsional viscous damper. So and a damper is also attached over here. Okay, a viscous damper is attached to form a single degree freedom torsional system. The scale is graduated in equal divisions. The equilibrium positions of the rotor corresponds to 0. So here it is the mean equilibrium position. Okay. Okay. When a torque of 2 into 10 raised to minus 3 is applied, so initial torque of m0 is applied. Okay, that is 2 into 10 raised to minus 3 Newton meter. the angular displacement is found to be 50 degrees. So when initial torque is applied, the what is say deflection is 50 degrees. With the pointer showing 80 divisions. Okay, so 50 degrees corresponds to 80 divisions. Alright, and when the rotor is released from this position, the pointer swings from, so suppose this is the positive side, this is the negative side. So on positive side it goes up to say total say 50 degrees. So 1 2 3 4 5, so this is 50 degrees. Okay, so now it is released. So then it goes to minus 20. 1 2 so 5, 10, 15, 20. So it goes to minus 20, and then again it swings back and it comes to plus 5. Okay, so do you understand what is happening? All right. So first it goes to plus 80 divisions, then it goes to 20 divisions, and then again 5 divisions, like that. Okay. Find the mass moment of inertia of the rotor, the undamped natural time period of the rotor, torsional damping constant, and the torsional spring stiffness. Okay. So let's summarize the data. M0, that is the initial torque applied. It is Q into 10 raised to minus 3 Newton meter. Theta 0 is the angular displacement. That is the initial angular displacement is 50 degrees, or that is 50 into 5 by 180, that is equal to 0.87 radians. Okay. So it's not, I don't know, okay, so K torsional will be M0 divided by theta 0. So you have to find the torsional constant of the spring. So divided by 0.87, so that is 2.29 into 10 raised to 3, 10 raised to minus 3 Newton meter per radian. Okay, and time period of damped vibration is given as 2 seconds. All right. Okay, so this is the summary of the data. Now let's plot what is happening. So initially, see, this is the mean equilibrium position. Okay, so initially it is taken up to by applying initial torque of M0, it is taken up to 80 divisions. Okay, then it is the spring is released. So here it goes to 80 division. Then it is released, so it swings back to 20 minus 20. Okay, and then again it swings back to on the other side to plus 5, like that. So it goes from 80 to minus 20 to plus 5. All right, and the time period to complete this complete oscillation is 2 seconds. I hope that clarifies. Any questions?
No, sir, we are getting it.
All right. Okay. So now let's first find out the logarithmic decrement del. Will be natural log of theta 0 by theta 1. That is equal to twice phi zeta upon 1 square root of 1 minus zeta square. So theta 0, see, theta 0 will be proportional to, we don't really need to convert this everything into degrees. Theta 0 will be proportional to 80 divisions. Okay, and theta 1 will be proportional to, that is after 5 divisions. All right, so substitute that. So del is equal to natural log of 80 divided by 5 into twice phi zeta upon square root of 1 minus zeta square, and find out zeta. Give me the value.
Sir, 0.4038.
0.4038. Zeta is equal to 0.4038. That is the damping ratio. Right. Alright, so this is the damping ratio. Next, what is asking the question?
Damp frequency and undamped.
Okay, so damp frequency is omega d they have asked. So it is twice pi by TD. So that is nothing but pi radians per second because TD is 2. Alright. And undamped natural frequency, what will be natural frequency? Omega d.
The relation
Omega.
between omega and omega d.
Pardon? Omega d is omega n into square root of 1 minus zeta square. Zeta is already known to you. What is zeta?
Sir, 0.04038.
Okay. So substitute and tell me the value of natural frequency.
So 3.434.
Correct. Okay. So natural frequency is 3.43 radians per second. That unit will not change. Okay. Now they also ask you to find out the
Time period.
undamped time period. Okay. So what will be that?
2 pi by omega n.
Twice pi by omega n.
Yes.
So find out.
Sir, I am getting 1.82969.
1.89 seconds. Alright. And also calculate now. Last thing they have asked you to calculate the MI of the rotor. So how to calculate that? Anybody other
We
than
know
Abhishek?
omega n equal to the root of k equivalent by alpha. इसके find कर
Who is
सकते
the answering?
Sir, Abhishek Mishra.
Other than Abhishek, if anybody else wants to answer? All right. So as currently said by Abhishek, so omega n is k torsional divided by I. So that will give you the value of I. So find out the value of I and tell me the answer.
One point 94 into 10 power minus 6.
Who is that?
Harshal sir,
Harshal. SAP ID?
36.
36. Okay. All right. So you got the value of I. Now last thing there I think I have asked is the damping constant. So how to find out?
So zeta equal to C by CC. I mean
Constant and
CT by
damping
CC.
ratio are the same thing. So yes.
So C by CC. I told us zeta.
Zeta is equal to C torsional divided by C torsional critical, right? Or so no sorry. Damping constant means C torsional they have asked, not the ratio. Sorry, I'm sorry. So this is CT, which that is the damping constant is same as damping. What is it? Damping coefficient. Okay, damping constant and damping coefficient are the same thing. Okay. So C torsional is zeta into C torsional critical. So that is zeta into 2 into I.
Omega n natural frequency.
Okay, 2 into I into omega n. All right. So you know I, you know omega n, you know zeta. So substitute and tell me the value of CT. Hello.
Sir, I'm getting for 5.37 into 10 raised to minus 4.
Yes, it is 5.32
37.
into 37.32 I am getting into 10 raised to minus 4 Newton meter second per radius. Correct? Correct? Okay, so that completes the what do you say, the today's lecture content. Now go to the quiz and open up the first quiz link. Let me activate the link from my end also.
Sir, do we have to do the both quizzes today only?
Yes, now I am giving you some half an hour, 20 minutes to complete the both the things. So first start with part A and just click on the link and let me know if you are able to see the quiz.
Yes, sir. We can see.
Okay. Start solving that and submit it. Both the quizzes are to be submitted before the lecture. So all the questions are from the notes, today's notes. So with reference to that, all the questions are asked. Okay. Just enter the values without say units. That will give you the answer. When we submit, you will use the units or action.
Hello, sir. Hello, sir. Sir. Sir.
तो फर्स्ट वाले के लिए आंसर रेडियन पर सेकंड में लिखना है कि हर्ट्ज में?
Hello, have you submitted the first quiz?
So in the
Yes.
first quiz, the first question you have
still
to write in
working.
radians per second or hertz.
What is asked given in the question?
So it's asked hertz, but I think the answers have been, I guess, confused for hertz. Can you check it
No, no.
once,
See,
please?
answer you still don't know, na?
So it's
Have
giving
you
the
submitted
answer
the
after
quiz?
submitting. Yes, sir.
But you have submitted all the questions.
Yes, sir.
Okay, okay. I will open the second quiz. Wait, just hold on. That's okay. You can convert the units and just check.
So because the answer that is mentioned there, I'm getting that in radians per second.
So fine. You're getting- Hello. Yeah, I've enabled the second quiz. Just open it.
Can you also confirm the answer for the first question? There's a doubt.
First question for part A.
Yes, sir. So the question in it's written, you have to answer in hertz.
तरी इकडे नेटच नाही. हा. Answer you're getting 1, na? Hello.
One is in
Hello.
radian per second.
1 radians, that is correct.
So because in question, if you have to written, you have to answer in hertz.
Yeah, ignore that. Hertz, that is you have to divide it 1 divided by
2 by
twice
pi.
pi. So
1 by
ignore.
2 pi. Yeah.
So 1 hertz is correct.
So I wrote according to like the 2 pi, 1 upon 2 pi. So it's coming.
Correct. But it is given in radians per second. So that is fine. Alright,
So
so
we have to-
are you able to access the second quiz?
Yes, sir.
Okay, so I'm now disconnecting now. I will be on the phone. याच्यावरती नेट चालत नाही याच्यात. आवाज आला. हॅलो, तुझं नाव काय? Submit the second quiz and you can log off. Okay. Excuse me. Wi-Fi चालत नाही तिकडे. हा, Wi-Fi. ते पीसी चालू व्हायलाच किती वेळ लागते म्हणून लॅपटॉप आणलं. हा. त्याच्यात ओपनच होत नाही का पेज? ठीक आहे, चालू केली काहीतरी अपडेट बिपडेट. अच्छा, ह्याच्यावर केलं ना काही. हॅलो, हे वायफाय चालत नाही इकडे तोपर्यंत वायफाय. Hello, all of you are able to access the link.
Yes, sir. Yes, sir.
The part B link is it accessible?
Yes, sir. Part B is accessible.
Okay, you have to just submit the quiz and that's all for today.
Okay, sir.
If you have any queries, you can just send me a message or send a post on the chat box. All right, that's all for today. Okay. कुठले वेगळे आहे ना? इकडे कनेक्ट करायला आणि तसं डायरेक्ट कनेक्ट ऑलरेडी कनेक्ट म्हणजे स्पीड नाही ना. त्याच्यावर चालतं करतो पटकन असं हे करू का असू दे हे पण करून ठेव. याच्यावर झालं ना, याच्यावर झालं ना त्याच्यावर शिफ्ट करतो. टीम सॉल्व ओपन होतो. टीम सॉल्व I do not trust this system. बँकेत पण जातो ना, सगळं घेऊन फिरायला लागतं. पॅन कार्ड, आधार कार्ड, फोटोग्राफ इकडे पण सगळं घेऊन फिरायला. पाऊस कमी घेऊन असतो. मीटिंग everybody. मीटिंग शेड्यूल नाही केली. मीटिंग मीटिंग मला शेड्यूल टायमिंग काय Huh? 9:55 till 10, 2.5 drawing. Okay, 1 o'clock. With 1:30, na? 1:30. ड्राइंग वाला दूसरा ना सही बता एक्चुअली जॉइन ना हाँ सर ना पोस्ट मीटिंग में दिसो तो एक टीम का ना जैसे रीजन करो तो रीजन टीम का ना जैसे क्लिक है ड्राइंग से इथे जॉइन नाही नाही G3 पाहिजे चला हो लॅपटॉप घेऊन The question paper is available. All of you check, the question paper is available. All of you switch on the cameras. 39? Oh. Hello, some wrong people have joined the meeting. How is that possible?
Sir, this is vibrations class. You
Huh?
have. Sir, this is vibrations class.
अरे रे रे क्या है? Okay, you can leave, huh? You guys can leave. Hello. Hello.
Yes, sir.
Yeah, you can leave. Just submit the quiz. If you can submit it after the lecture also. If you are not finished. All right, that's all for today. Thank you.